Hello and welcome to the Hydrocarbon Engineering Podcast, the podcast series for professionals in the downstream refining, petrochemical and gas processing industry. I'm your host, Callum O'Reilly, Senior Editor of Hydrocarbon Engineering. In this episode, I'm joined by Rasmus Rubycz, Markets Manager for New Energy at Atlas Copco Gas and Process. And we're going to be talking about heat pumps as an industrial technology that is gaining greater attention as a result of the increased drive for sustainability. I hope you enjoy this episode.
The Hydrocarbon Engineering Podcast is brought to you by Owens Corning Foam Glass Insulation. From managing vapor drive and mitigating corrosion risk, to maintaining thermal performance and supporting safety on the job site, the insulating system plays a critical role in high-performing hydrocarbon processing facilities. Learn more about how foam glass insulation contributes to the design of high-performing insulating systems at cryogenic facilities at www.owenscorning.com/foamglasslng study. That's www.owenscorning.com/foamglasslng study.
Welcome, Rasmus, and thank you very much for joining us to discuss the content of a recent white paper that you wrote for Hydrocarbon Engineering.
Thanks for having me, Callum.
Now, your white paper, titled The Heat Pump Way to Sustainable Process Heat, considers how the decision to invest in an industrial heat pump means a further step towards the decarbonisation of industry. And I'm really looking forward to diving into the details on this with you. But before we get started, Rasmus, please can you introduce yourself to our listeners and tell us a little bit about your current role at Atlas Copco?
Absolutely. So my background is process engineering. I studied process engineering in Cologne. And when I joined Atlas Copco as a project engineer, I was working hands-on the products we're making in our Cologne facility. Over the time, I seemed to have some good ideas. So therefore, I managed it to enter the marketing department. And I'm now firmly in the role of being a market segment manager, as you said, for New Energy, what covers a wide portfolio of products, steam compressors, industrial large-size heat pumps, energy storage applications, energy recovery, you name it. And as you can imagine, of course, those projects, they have a high tide right now because everybody is speaking about decarbonization. And I'm really thrilled by merging our technology with some good ideas and, of course, sustainable energy in the future.
Thank you, Rasmus. So to start off with, can you talk to us about how big the challenge is of electrification of process heat in the process industry?
Yes, sure. Generally speaking, the industry and especially the way the industry is providing heat to various processes has grown over decades, and it was always the same way. You burn something, no matter what temperature level you need, be it like very low level temperature for heating substances and catalyzing chemical reactions, to super high temperature for smelting steel and aluminum and so on. Flames are the universal plan A, and they have been always in the past. Now, looking at this, the whole infrastructure is built around using fossil fuels. And if you want to use energy, especially green electricity, in a sensible way, then you have to see how well you can blend those existing assets and infrastructure with new technology. And speaking about the industrial heat especially, you have to live very often with high temperature needs. And that's the challenge, especially when speaking about industrial heat pump application.
In what ways will electrification of process heat make a significant impact?
If you look at the bigger picture, then you can say that roughly 25% of the whole CO2 emissions in the world origin from industrial processes. It's not all the heat generated for the processes, it's the general industry. But if you look then into the share of industrial heat, you can see that 1/3 of this quarter is originating from industrial process heat in a range that could be handled by heat pumps. So you can say 1/3 of 1/4 of the world's CO2 emissions are something that can be lowered or even completely get rid of if you would consequently roll out industrial heat pumps in the industry. So the leverage is pretty big.
So, what are the different technologies that Atlas Copco can bring to the table when it comes to sustainable process heating? And what do you think differentiates your technology?
Of course, as one of the world-leading manufacturers of large-size and industrial grade and design the turbo compressor equipment, we can, of course, bring our expertise of decades of building those machines to the table. And the cool thing is that for many applications where you can use those technologies like industrial heat pumps and steam recompression systems, you always have a centerpiece that is a compressor. And if you want to move large quantities of heat, then you need a large compressor, of course, and ideally a very high efficient and reliable one. All assets and all aspects of a product that we are proud of, it's in our DNA and heritage, building machines that are built to last and to work in a highly efficient way. So to your original question, what can we bring to the table here? We bring the heart of an industrial heat pump and the heart of an industrial steam compression cycle to the table to electrify your process.
So, Rasmus, I guess my next question would be, is your technology really zero carbon?
It depends, first of all, very much on the way how you source and produce the electricity that drives the system. If you use all green or all sustainable zero carbon electricity for this, so must be a zero carbon source or very low carbon source, then of course there are no direct emissions from operating our equipment in terms of CO2 emissions. Our compressors are usually driven by electric drives. That means if you use green or carbon neutral electricity, there are no direct emissions. Of course, making the machines requires smelting metals, manufacturing, and so on. While we try to mitigate, of course, the CO2 emissions along the manufacturing process, still there are some emissions, but the majority of the CO2 emissions, they result from operating the equipment. So if the machine is operated with green electricity, then there are no direct emissions.
And how mature is the technology? Are you able to give us any examples of its use within the industry?
Yeah, the turbo compressor technology itself is a technology that is really well established, with the first wide-scale use of the technology that we offer, the integrated geared radial turbo compressor from the 1950s. And over the time, the industry adopted gradually more and more this technology in areas where it has not been used before, starting from air separation, where there is a high IMARC and focus on the efficiency of a process. It grew into other areas, and we have seen the first wide-scale application of our machines in this direct application, namely industrial large heat pumps in the 1980s, with Scandinavia being one of the front runners introducing large-scale heat pumps. And believe it or not, we have still machines running from the mid of the 1980s with unchanged main components that are 40 years later running in everyday operation. That's one of the best examples that you can ask for to prove how long the lifetime and the life expectancy and durability of those machines are. So is it a proven technology? 40 years of operation and longer even, that prove, yes, it is a mature technology.
So you just picked up on something that I was just about to ask you, actually, Rasmus. What do you consider to be the typical lifetime of the equipment?
At least 30 years, because we say that, of course, if you decide for a high value, high price product like our compressors are, then of course it's not something like a consumer good that is used for a couple of years and then thrown away or recycled. The machines that we offer, they are more like critical infrastructure in whatever process you install it. And the lifetime of those assets is typically beyond 30 years. And that's the reason why we are making our machines as well for a lifetime like this. But it does not mean that after, like what I said, 30 years, we are no longer supporting those machines, because every piece we do in our factory is very much made to order it's as well for us no stretch making spare parts on demand for machines that are older than 30 years. If you want to operate the machine for a long time, we will not limit you. We will not stop you from doing so. In contrast, we will rather encourage you keeping the machine online. And one point when you say, okay, now we need to think about something new, then we are, of course, there helping you. Maybe you can keep the old machine running with some tweaks. We do that as well.
So, Rasmus, can you talk to us about how the technology performs in comparison to hydrogen and direct electric heating?
Yes. Now that's a great example of how sometimes you see the solutions maybe a bit in a biased way, or maybe too glorious way, that hydrogen is the universal energy messiah. I hope I'm allowed to say that, or the silver bullet that kills all the energy crisis in the world. But one uncomfortable truth is that hydrogen is not an energy source; it's an energy carrier. That means it's not something you can mine in the natural resources or can capture out of the air. You have to generate it. And if you generate hydrogen from a kilowatt hour of sustainably sourced or green electricity, you will end up, after you've turned the electricity into hydrogen, with less energy than you originally put in. Why is this? Because the electrolyzer is losing efficiency along the way. And from 1 kilowatt hour green electricity, you will eventually have something like 0.7 kilowatt hours of chemically bound energy in the hydrogen. And if you turn that into heat by combusting, by burning the hydrogen in an oven or furnace, then you maybe end up with 0.6 kilowatt hours. In contrast, if you use the direct electric route, like with electric resistant heaters, some very straightforward way, like the electric boiler you have at home maybe, then the conversion ratio is much better. It's almost 1-to-1. That means for every electricity kilowatt hour you put in, you get almost 1 kilowatt hour of heat out. Now, these all are direct uses of electricity into heat. The heat pump, in contrast, makes something fundamentally different. It's more like you pay the heat pump for lifting already existing heat. That means it's not you turn the electricity into heat, you use the electricity to pump the heat. It's more like an escalator for heat. So that's the big trick why a heat pump uses the electricity in a much more sensible way. And it can be as good as 6-to-1, so to say, maybe even 8-to-1 for some technologies. For 1 kilowatt hour you put in a heat pump, you get 4, sometimes 6 kilowatt hours of heat out. That is called the COP, the coefficient of performance. While hydrogen will always give you less than 1.
So Rasmus, how easy is it to integrate the process into existing plants as well as new plants?
Of course, if you do something from the scratch, then it's always easier to consider it from the beginning. The big trick is always, of course, integrating it in existing assets and plants. And especially chemical plants and larger factories with a tradition already on a local site. They sometimes grew over centuries, sometimes even longer. Like when you look at those classic large chemical companies, sometimes date back to the mid of the 1850s or so. You can imagine that this looks like a forest growing over the years of pipes and columns and distillation towers. And it's hard finding a free spot for a heat pump that, of course, is building a bit larger than just a straightforward fossil fuel-fired boiler. But there are ideas. If there's no space, you can use cooling water systems as the heat source. Then you can locate a heat pump installation a bit more in the outskirts of the plant. While if you have the space, integrating it right in the heart of the plant, you maybe can use direct steam compression, what is always the best way of using the heat directly. So means no matter if it's an existing plant or a new plant, you can be sure there is a way integrating it. So there's no excuse saying we cannot do it.
So my next question, Rasmus, would be, are these systems always viable when we're considering technological and economic feasibility?
Very good question. And I hate to say it depends, but in this case, really it depends, because you can imagine if it's an economic decision going for this technology, it's always, or nearly always, a decision that is based on return on investment and interest rates and so on. So you can say what is essential that a heat pump is economically viable, that the output heat, the output product, is less in price than the previous fossil fueled option. And this is very often the case if there is a good balance between the price of electricity and the price of the fossil fuel. Of course, if you're in an area of the world where you have to pay for CO2 emissions, then you have to factor that in as well. Let's say an example, electricity is 10 cents a kilowatt hour and natural gas is 5 cents a kilowatt hour. Then you have a 2-to-1 ratio between the two prices, and the efficiency of the heat pump typically is better than 2. That means in this case, you would have a positive business case if your electricity is now 20 cents and natural gas is 5 cents. Then you may be at the break-even point of this. So it's very much depending on your expectations in terms of return on investment and the balance between electricity and the alternative fossil fuel option.
Based on your answer there, I was wondering if you're able to provide typical values for efficiency of operation, OPEX and CAPEX, so that our listeners can carry out some basic studies for themselves.
Of course, yeah. Maybe let's first give some typical estimations for efficiency of heat pumps and steam compressors. You can say if you have a heat pump that is taking heat, for instance, from a cooling water network and is producing low pressure steam from it, then we speak very often about a 100 Kelvin or 100 degrees C temperature lift. Say you start at something like 20 to 25 degrees cooling water temperature and you want to go in the low pressure steam area. It's about 100 degrees. A good heat pump that we would offer together with our EPC partners would provide at least a COP of 2.5 for a lift of 100 Kelvin. Sometimes a bit more. So let's say between 2.5 and 3 is a good COP of a heat pump. Then, knowing, of course, the electricity price you have to pay and the price of your fossil fuel option, you can do the math yourself. And typical companies, they request return on investment times between 5 and 7 years. We've seen examples where this is working. Of course, it's hard to throw out numbers like euros per kilowatt, but on larger installations on a turnkey basis, we reach very often specific prices of less than $1,000 a kilowatt thermal power output of the heat pump on a turnkey basis, including buildings and so on. So take this below $1,000 a kilowatt as a guideline if it's a large system in the range of more than 10 megawatts. COP of 2.5 for 100K lift, and then this figure I just mentioned, together with the COP and the electricity prices, gives you enough indication for making an investigation whether or not a heat pump is something that can be sensibly used in your process.
Great. Thank you so much, Rasmus. I really appreciate you taking the time to answer our questions for us today and for providing a preview to your really interesting white paper. This is a topic that's really fascinating and we're seeing a lot more of. So we really appreciate your time with us today.
Especially when adding to this another layer, we spoke a bit about the role that hydrogen plays in the infrastructure. Let me close this one off with a bit of a positive remark on hydrogen. Of course, it's not just that hydrogen is inferior to the performance of a heat pump. A heat pump always needs to have power from the grid. So if we are more and more relying on renewable electricity, then of course we will have times in the year where there is not enough electricity given by PV, wind, and other options. For that, of course, hydrogen is something that makes a ton of sense because you can store it. Not like the heat pump thermal power, you cannot really simply store that. Making that hydrogen is not efficient, as I said, compared to the heat pump. But when you make that hydrogen, it gives you lots of waste heat. So integrating a heat pump in a large hydrogen plant and recovering that heat is also something that we will see more often in the future
I think this is exactly the point, though, Rasmus, that you make, is that these technologies working hand in hand together. There's no one silver bullet, as you already said. So we need as many different innovations to solve the decarbonisation issue. My thanks again to Rasmus for joining us for that really interesting discussion on sustainable process heating and the benefits that an industrial heat pump can offer. If you're interested in learning more about this topic, I'd encourage you to head over to our website and download a copy of Rasmus's white paper. Simply visit hydrocarbonengineering.com/white papers and follow the on-screen instructions to access your free copy. I hope that you enjoyed listening to this episode of the Hydrocarbon Engineering Podcast. Please rate and review and subscribe wherever you get your podcasts to ensure that you never miss an episode.
The Hydrocarbon Engineering Podcast is brought to you by Owens Corning Foam Glass Insulation. From managing vapor drive and mitigating corrosion risk to maintaining thermal performance and supporting safety on the job site, the insulating system plays a critical role in high-performing hydrocarbon processing facilities. Learn more about how foam glass insulation contributes to the design of high-performing insulating systems at cryogenic facilities at www.owenscorning.com/foamglasslng study. That's www.owenscorning.com/FOAMGLASLNG study.